Okay, welcome to the second video then on forces and braking, and this is actually the final video in this whole little section. So I want to start off here with a recap of stuff that you did earlier on in the course about thinking distance, braking distance, and stopping distance. Just remind you of the definitions and just make sure that you are happy with these. So I'm going to advise that you write notes as we go, and actually the first thing you can do before I write these down is see if you can remember them yourselves. So thinking distance then, if you remember the thinking distance, it's the distance travelled during the driver's reaction time. So while the driver is actually reacting to a hazard, reacting to the fact that maybe there's something in the road, the car will obviously travel a certain distance, and that is the thinking distance. Okay, the next one then, braking distance. Well, if you remember, the driver is then going, once they've travelled this distance, this thinking distance, they're going to hit the brakes. And the distance that they travel while they're actually braking, that's the braking distance. So our definition, this is the distance travelled under the braking force. In other words, while the braking force is actually acting, how far does our car travel? And then the stopping distance is just those two added together. So it's the total of the thinking distance plus the braking distance. And if you remember, there are lots and lots of factors which will affect thinking distance and braking distance. One key factor, though, there was only one factor really that affected both of those quantities, the thinking and the braking distance, and that was actually how fast you were travelling. So the speed is the only thing that affected the thinking distance and the braking distance. Now, you often will see, if you look in, say, the highway code or somewhere, you will see tables a bit like this. And you can see there that going down the screen, you've got different speeds, so 20, 30, 40, 50, 60, 70 miles per hour. And the arrows show the thinking distance in blue and the braking distance in red. And as you would expect, you can see that as the speed goes up, both the thinking distance and the braking distance go up. But if you look carefully, you can see there is a difference in how they go up. The blue arrows, that's the thinking distance, well, look, they're going up by the same amount each time. Every time you increase by 10 miles per hour, look at the numbers, the thinking distance goes up by 3 meters. But the braking distance doesn't. So the braking distance, as you increase the speed, the braking distance is going up by more each time. So from 20 to 30, it goes up from 6 to 14. That's a difference of 8. Then from 30 to 40 miles per hour, it goes up from 14 meters to 24 meters. That's a difference of 10 meters. And so on. And so these are different patterns, and we do need to be able to think about why that is happening. Now, this is not the easiest thing to get your head around. But let's see if we can think about why that might be. So we'll start off by focusing on our thinking distance and actually thinking about, well, why is it that the thinking distance goes up, what I suppose we'd say is linearly? Why is it going up by the same amount each time for the same increase in speed? Let's go back to actually what we're meaning by thinking distance. So thinking distance is the distance travelled during the driver's reaction time. And so that distance is just going to be equal to the speed times the time. That's a rearrangement. Look, of speed is distance over time, so distance equals speed times time. Now, this time, that's going to be the reaction time, isn't it? That's how quickly, the driver reacts. And so for any driver in a certain situation, on a certain day, for example, that reaction time is going to be the same. And so you can see, look, if you then got, say, double the speed, you're going to have double the thinking distance because that reaction time stays the same for any given situation. And so if you actually were going to draw a graph of thinking distance against speed, so if we have speed here, and then we have thinking distance on the y-axis, I just said, didn't I, that doubling the speed doubles the thinking distance. Now, when you've got 0 speed, you're going to have 0 thinking distance. So that's therefore going to be a straight line going through 0 like that. And we can use the term directly proportional. Straight line through 0, you should be familiar with. That suggests and tells us that thinking distance and speed are directly proportional. So that is actually a conclusion we can write here. So thinking distance is directly proportional to speed. And what that just means is that if you double the speed, you double the thinking distance. And on a graph, it's a straight line through the origin. Okay, and that explains why the thinking distance goes up by the same amount each time. Right, let's dig down a little bit then into the braking distance and see if we can work out why that's different. Okay, now, I'm going to give you a word of warning straight away. This is a little bit more difficult. And if you don't quite follow this straight away, please don't worry. Let's actually think about the braking distance. Now, this is coming back to the example we had with this truck in the last video. Okay, and we had an example with it, and we talked about it stopping and looking at the work done by the brakes to transfer the kinetic energy. And so what we had was the work done, this is by the brakes, equals the kinetic energy which our car had to start with. Now, of course, we're thinking about braking, we're thinking about the braking distance. That's the situation we're thinking about. The work being done by the brakes while the braking force is being applied is transferring the kinetic energy that the car had. So if we actually put here our equations in, work done was force times distance, kinetic energy, half, times mass, times speed squared. Now, the force, well, that's the braking force, so that's going to be constant all the time. The mass is going to be constant all the time. And so what we get is this relationship that distance, so the braking distance, is not going to be directly proportional to the speed anymore. It's going to be directly proportional to the speed squared. Okay, so the braking distance is directly proportional to speed squared. Okay, so what that means then is not that if you double the speed, you will double the braking distance. This time what it means is if the speed has doubled, so the speed has gone up by a factor of 2, so times 2, the braking distance will be times 2 squared. So the braking distance would be 4 times as big. So this time we have got, if you double the speed, you get 4 times the braking distance. Okay, similarly, just as another example, if you had 3 times the speed, you'd have 9 times the braking distance. Okay, it might be clearer actually here if I write double as 2 times the speed. Alright, and the reason for that, 2 squared is 4, 3 squared is, oops, sorry, that's not quite in shot, 3 squared is 9. Okay, now, even if you don't understand at all where this comes from, it is worth remembering the bit in red and kind of remembering roughly what it means. Now, if we were going to draw a graph of this, we drew a graph of the previous one and we showed it was a straight line. This one is not going to be a straight line anymore. This is the pattern that you would see. You would see a curve. It's a squared graph. Okay, you would see a curve because that braking distance is going up by more each time you increase the speed, in this case by 20 kilometers per hour. Okay, now if we sort of show both of these together, okay, so the red line there, that's the thinking distance, the green line is the braking distance, and the blue line is showing them added together. All right, and so that's showing you how the thinking, braking and stopping distances go up. Just to sort of summarise it all again, thinking distance is directly proportional to the speed. Braking distance is directly proportional to the speed squared. So just to summarise then, thinking distance is directly proportional to speed. Therefore, if you double the speed, you double the thinking distance. Braking distance is directly proportional to the speed squared. So if you double the speed in that case, you have 4 times the braking distance. Right, let's look at an example then, just to show you how this can come up in questions and just show you how to approach it. So hopefully if it does come up, you'll know what you're doing and you'll get the marks. So a driver performs an emergency stop to avoid hitting a monkey in the road. It's another really common situation. His thinking distance and braking distance are both 5 metres. Estimate his total stopping distance if he had been travelling 3 times as quickly. Right, here's the situation then. There's our car. It's got its thinking distance of 5 metres, so that's while the driver is reacting. Then it's got its braking distance, and it stops just in time to avoid hitting the monkey. Now the question says, if he'd been travelling 3 times as quickly, what would his total stopping distance be? So here, look, the total stopping distance would obviously be 5 plus 5, which is 10 metres. But now we're saying then that his speed is 3 times bigger. So the speed is now 3 times bigger. And we're thinking about what happens to these 2 different numbers. So let's think about the thinking distance first of all. Well, remember, thinking distance is directly proportional to speed. So if the speed is 3 times bigger, that means the thinking distance is 3 times bigger. So that's also 3 times bigger as well. So therefore, what we've got is that that's going to be 3 times what it was before, which is 5, giving me 15 metres. Now what about the braking? Well, the braking distance, remember, is proportional to speed squared. And so if the speed is 3 times bigger, that means the braking distance is 3 squared times bigger. Okay, now 3 squared is obviously 9. And so that means that our braking distance is now 9 times bigger. So we've got 9 times 5, which is 45. And so our new total stopping distance is going to be 45 plus 15, which is 60 metres. And so you can see there that you've got a speed 3 times bigger, but our total stopping distance is now 6 times bigger. This is why they say that you need to keep your speed down when driving. And this is why just changing your speed from 30 miles per hour, slowing it down from 40 miles per hour, say, down to 30, can have such a big difference on your overall stopping distance. But the point of doing that example there is this. It's this idea that thinking distance is directly proportional to the speed, braking distance is directly proportional to the speed squared. Okay, I hope that makes sense. That is one of the certainly the most difficult areas of this topic. So if you kind of see what's going on, that's brilliant. So that's actually the last video in this topic. That's the end of the topic. I hope the videos have been useful. And so stay safe, and I will speak to you all very, very soon.